Hello, I'm hoping people can hear me. We'll be starting the webinar shortly. This is Curtis Caldwell from the Radiation Safety Institute of Canada, and we're just going to be waiting for a few more to join. So it'll be just a few more minutes. Hello, it's Curtis Caldwell here from the Radiation Safety Institute of Canada. I'm hoping that you can hear me, and we're going to be starting the webinar fairly shortly. We're just waiting for a few more people to join. Okay, so at this point, I'm just going to talk about the webinar functionality. The audience is going to be in silent mode. That means I'm going to be the person talking, and you won't be able to talk back to me at this point. We won't have the webcam on, which is an advantage for you, I'll say, or for all sighted people. The audio, I recommend using the computer audio first. It seems to be best. If that doesn't work, then there's a telephone call-in number I think you were given, but it seems that the computer gives the best sound quality. Now, there is a chat feature where you can enter comments, but it's really the questions feature you might want to use. If you want to ask me some questions, and I'll try to answer at the end of the webinar, if you could type them in the questions section, I'll take a look at them at the end and try to answer those questions audibly for everybody afterwards. Now, a copy of the slides will be available as a handout, and it's available in the handout section. So you should be able to download that at any time now. Now, after the webinar, when the recording becomes available and has been added to our website, there will be a link to the webinar, and that will be sent to all the participants. Now, people are still signing in, but I would like to gather some information about the people participating now, if possible, particularly your fluoroscopy experience. So we're going to use the polling feature of the webinar system to ask you a couple of questions. All the answers are confidential. We don't know who answered what. So it's just 3 simple questions, and they'll come up one at a time, and we'll try to give you the what everybody has answered. So I'm going to try the first one now, and whoever has a chance to answer would be appreciated. So I'm just going to select one and launch it. So I'm hoping that you see this. If you could answer this, pick one of the things that's closest to what you are or your profession, it would be much appreciated. So I'll just give you just a couple minutes or a minute or so to decide. Okay, and I'm just going to share that result with you. I think it does come up there. So it's interesting. It looks to me like we've got a lot of MRTs, a few nurses, and a few others, but not radiologists or cardiologists, which is fine. I'm going to just go to our next one then. So I'm hoping you see this one as well. And a question about using eye protection is here. That's kind of an interesting one for me, kind of a pet interest of mine. And it looks like a good percentage don't use eye protection, but it might not be applicable to you. And then I'd just like to see if you have an idea of this one. The longest beam on time you've been involved with, if you give that some thought. I know that one's kind of a hard one. I know some people didn't vote, probably because it's hard to recall. But it looks like there's some fairly long beam on times that were out there. So those are our three polls. Now, and I guess we can try to get started then. So hopefully you enjoy the webinar. So my name is Curtis Caldwell. I'm the chief scientist at a nonprofit institute, the Radiation Safety Institute of Canada. And I'm going to talk to you today about radiation safety in fluoroscopy. So in this talk, we'll review risk due to exposure to ionizing radiation, such as X-rays. We'll talk about what adverse effects we're actually trying to prevent. We'll then talk in particular about equipment used in fluoroscopy. So what type of equipment, and in particular, what aspects of that equipment help keep yourself and patients safe. We'll talk about managing dose to the patient. Obviously, the patient is in the beam. We're doing something, a procedure on the patient to presumably help their health. So they are going to get radiation dose. So it's not a question of eliminating all dose to the patient, but we should be able to manage the dose to appropriate levels. Reducing staff dose, which is certainly related to patient dose, is a crucial thing that we should be doing. And there's certainly ways that we can reduce staff dose. And I've certainly seen different places where we're not doing all we could do or should do to keep the staff dose in fluoroscopy as low as reasonably achievable. I'll then try to summarize or come to a conclusion. So first of all, as you all should be aware, fluoroscopy suites are a fairly high radiation exposure work area. Certainly, probably the highest area in a hospital where people are actually working. Now, there are other areas within a hospital that might be higher exposure areas, but people aren't actually in those areas during the exposure. So these are areas that may have relatively high exposure. And as shown here, you can have fairly high exposure rates from maybe about 0.5 to 10 millisievert per hour exposure rates or dose rates. Now, I just want to point out that I'm going to use millisievert and milligray interchangeably here, and I think for X-rays that's a reasonable thing to do. So if I say millisievert or I say milligray, they're still similar units in this case. Now, occupational risk for fluoroscopy. Situation is we actually are working in an area with an open X-ray beam. We're working close to radiation sources. Our exposure times can be long, and therefore there is potential for high exposure to workers. We need to be conscious or be aware of the fact there are two groups that we have to consider radiation exposure to. There's the workers and there's the patients. So the workers may get high doses, the patients may get extremely high doses within fluoroscopy. We need to be aware of what we can do to reduce those doses or keep them to a reasonable level. Now I'm going to just step back to the very basics to start. So I'm sure many of you are aware of this, but ionizing radiation, what does it do when it interacts with an atom? So when radiation such as an X-ray, which is ionizing radiation, strikes matter, it interacts with the atoms of the matter. Radiation that has enough energy to knock electrons out of orbit from the atoms it strikes is ionizing radiation. So if we imagine an X-ray coming in, it can knock off an electron, and then you have your electron, and you also have an ionized atom. And those can then cause subsequent damage to other atoms or molecules. So that's what happens. So now if we take a step up, what happens when radiation interacts with the body? So when radiation strikes living tissue, there are a number of possible outcomes that can happen. One is simply no damage is caused at all, and that is by far the most common thing to happen. Second thing that could happen is that damage to cells is then repaired. And we have great repair mechanisms in our body. So that's also pretty common. So there's no harm in either of those. So that's great news. But that doesn't always happen. There's also a possibility that there's damage to cells that lead to cell death. Well, that could be a problem. That could lead to what we call deterministic effects. If enough cells are damaged to the point of cell death, you can lead to some serious effects. The elephant in the room, though, is damage to cell chromosomes that is incorrectly repaired or mutated, because this is the thing we worry about. This is the possibility of inducing a cancer by a mutation of a cell. Very rare, but it can happen. So this is something we're trying to eliminate. So one of our biggest concerns in radiation protection is cancer. So the induction of cancer. Radiation exposure increases the probability of developing cancer. The probability increases with the dose received, and we assume it's a linear effect without threshold. This is called the LNT theory. Now, this effect is somewhat similar to smoking increasing the risk of lung cancer. We've all heard of that 90-year-old man who smoked 2 packs a day for 60 years and he didn't get lung cancer. Well, it's a statistical thing. Some people don't get lung cancer if they smoke a lot, but the more smoking you do, the more likelihood you're going to get lung cancer. In similar fashion, you might not get a cancer when you're exposed to a lot of radiation, but the more radiation you're exposed to, the more likely you're going to get a cancer. So the way we approach estimating these risks is based on a lot of historical studies of people who have been exposed to radiation. And based on those studies, we think that the risk of developing a fatal cancer as a result of exposure to radiation is approximately 4% to 1,000 millisievert or 1,000 milligray. Again, milligray, millisievert, equivalent in this case. So what if we consider 1,000 people who each worked for 50 years and each received 20 millisievert per year? The reason we picked that number is that's actually sort of the limit for some regulators in Canada, 20 millisieverts per year for X-ray workers. It's not every province, but some provinces have that. So the total lifetime radiation dose for these workers would be 1,000 millisieverts or 1 sievert. This population would then have an extra 4% chance of developing a fatal cancer. Now, we assume the baseline risk of dying of cancer is about 25%. So if you weren't exposed to radiation, or this population of 1,000 people was not exposed to radiation, you'd expect 250 cancer deaths. With the radiation, you expect 290 cancer deaths, so 40 extra. I want to point out that this number, the 4% per 1,000, is actually for fatal cancers. There's another 4% per 1,000 who would also have a non-fatal cancer, who would have to deal with that problem. Now, other than cancer, we're also concerned about deterministic effects. Acute exposures with high dose delivered within seconds, minutes, or days. Now, these effects have thresholds. It's not like the linear no threshold business with cancer. These things have thresholds. So below the threshold, you don't see the effect. Above the threshold, you might get a worse effect. So two of them I'd like to focus on, and they're cataracts and skin damage. So cataracts have a threshold. Below that, you won't get cataract. Above that, you're likely to get a worse cataract. Again, skin damage has a threshold. Below that radiation dose, you won't see the skin damage. Above it, you get worse skin burns. Now, one of the things I'd really like you to take away, if you can, is the issue of cataract. So cataract in fluoroscopy is an important issue simply because we now know that the threshold dose to produce cataract is lower than we used to think. We now know, based on international studies, that the threshold for cataract induction is only 500 milligrams. That's still a pretty big dose, 0.5 gray, but we used to think it was 8 gray or 8,000 milligray. Problem here is, for me personally, is that when I started out as a medical physicist many years ago, and people used to ask me who were getting into fluoroscopy, they'd say, well, do I need to wear eye protection? And I'd say, well, it doesn't hurt, but it probably doesn't help you that much because you're never going to get 8 gray to your eyes. Now, it's quite possible to get 0.5 gray to your eyes over a period of time at working in a fluoroscopy suite. So that is something I take personally, in that I was telling them not to wear eye protection, or it wasn't important to wear eye protection, whereas now I think, based on new data, it suggests that you should wear eye protection, particularly if you're the operator or the first assistant in a fluoroscopy suite. Now, regulations in Canada haven't really caught up to this in most provinces. Our current annual dose limits for the lens of the eye for designated X-ray workers is 150 milligray per year. That's based on that old 8 gray threshold. There's a new recommendation that will bring this down to about 20 milligray per year, a lot less. So I think we need to act cautiously about dose to our eyes. And it's certainly been shown. There have been people who've got cataracts in their eyes due to radiation dose. And this is an example of an interventional radiologist who had cataract. And certainly cataract's not as bad as getting cancer, but why risk cataract if we can eliminate the possibility by using appropriate shielding? Okay, so let's go to the fundamentals of radiation protection. The first concept is avoid acute effects. Avoid so high radiation doses that could cause injury or death. So that's step one. Secondly, though, you want to minimize the likelihood of radiation-induced cancers. And this is crucial. To do that, we want to keep radiation doses, radiation exposures, as low as reasonably achievable, a concept called ALERA. Now that means it's not enough just to keep your doses below the legal limits. You need to push those doses as low as reasonably achievable. And the way we do this, and every health physicist says these three words multiple times: time, distance, and shielding. So our principles in terms of keeping external radiation exposure minimized are: one, minimize the time you're exposed. Well, in fluoroscopy, that means minimizing the time the X-ray beam is actually on. Keeping the foot off the pedal when you don't have to have the foot on the pedal. The second concept is distance, and that's a great one, because it goes as the R squared. Now, what does that mean? That means if you're twice as far away as from the X-ray source, you get a quarter of as much dose. That's a fantastic use, a fantastic method of reducing your dose. Finally, shielding, and there's a variety of shielding we use, of course. When you're in the control area, there's the shielding of the lead glass window and the shielded doors, etc., shielded walls. The key one in fluoroscopy, though, is probably the shielding that we actually wear as personal protective equipment. So we need appropriate lead aprons, lead glasses, whatever shielding we can put on the side of our X-ray table, etc. So shielding can be crucial. So let's get a little bit more into fluoroscopy. So clearly, fluoroscopy machines, use an X-ray tube. The patient is exposed to the primary beam, so they're getting direct exposure primary, and that's at a much more intense level than the beam that we're being irradiated at if we're staff in the room. So most of the radiation others receive in the suite is from scattered radiation. However, radiation exposure to everyone, the patient and everybody else, is directly proportional to the on time of the unit. So what we need to do is keep the tube current, which is the MA, as low as possible, and keep the beam on time rather, in minutes as low as possible for our procedure. But this becomes complicated, unfortunately. There are a lot of issues. We want to get to low patient exposures, but we need to have good image quality. There are a lot of factors in modern machines to optimize these things. Really, to optimize image quality while keeping exposure low. This is not as simple as you might think, and it's probably different for different procedures that you're trying to do, whether it's in the cardiology suite, the interventional suite, or in any fluoroscopic situation. The choices are many, and we have to try to optimize things for our situations. Okay, so let's step back again. Equipment. You're going to see in your fluoroscopy room something like this, which is going to have a detector, and it's going to have an X-ray device, an X-ray tube. One of the first things that everybody should be aware of is which is which. And you might say, okay, yeah, of course I know which is which, but you'd be surprised how many people for the first time stepping into a new room aren't actually sure which is which, because actually you want to orient yourself to minimize your dose to keep away from the X-ray tube side of the object, the patient. So knowing which is your first step to protecting yourself. There are a couple of different main equipment characteristics. In the old days, we always used to have what are called image intensifiers, or IIs. We tend to still call them image intensifiers, even though most of the modern ones are what are called flat panel detectors. And they're new digital detectors. They have specific safety systems such as beam quality modulation through extra filtering, which I'll talk about in a moment. You can use pulse fluoroscopy instead of a constant beam, which also can reduce but doesn't necessarily reduce dose. You can use physical and virtual collimation, and of course we want to measure the dose to the patient if possible. So here's a bulky image intensifier, whereas a flat panel can be pretty thin. Now the good thing about flat panels is they really have higher sensitivity to X-rays. So if you think about it, if you have higher sensitivity, you can reduce the dose. They have better contrast resolution. Your images are going to be nicer. You might be able to do things faster. They have higher dynamic range. That could be good or bad. You have distortion-free images, so that might help with image quality, again, helping you to get the things done more quickly. And they have relative insensitivity to magnetic fields, which means you might be able to do it down the hall from that MR machine. So most of the fluoroscopic systems you're going to see, modern ones, are going to be flat panels. We're probably going to call them image intensifiers for a while, though, because that's our habit. Now, one of the ways we reduce dose to patients is using metal filters to reduce the low energy X-rays component in the beam. So modern systems will automatically set X-ray beam filtration according to patient weight and the angulation of the C-arm. So here's your X-ray tube. Your filters are going to go in here somewhere. And what this does, it keeps the skin dose low by removing the low energy photons from the beam. So if you'll recall, if you set your X-ray KVP to say 80, and if you had no filtration at all in the beam, which is actually impossible, we can't really do that, but if we could do that, the X-ray spectrum would look something like the dotted line. So with no filter, it'd sort of be a triangle. You'd have a lot of low energy photons and not too many high energy. What we normally do is we put a small amount of filtration, such as a 1 millimeter filtration here, and we get rid of most of the low energy photons. The reason we want to get rid of those is that they wouldn't get very far through the patient at all. They wouldn't contribute to the image, they just contribute to the skin dose. So it's very important to have that initial 1 millimeter filter. If you have a thicker patient, there's no use to having the other low energy photons between the 3 and 1 millimeter filter as shown, because again, they're not going to get through the patient, they're not going to contribute to the image, they're just going to give radiation dose. So the thicker the patient, the more filtration we're probably going to want to use. Now you might say, well, why don't we just go to the higher filtration to start? Well, for a thinner patient, we're going to get better images with a less filtered image. So that's why there's a bit of a trade-off here. Second concept for saving dose is pulse fluoroscopy. So pulse fluoroscopy can reduce radiation dose, especially by selecting a low pulse rate. But unfortunately, it's not actually guaranteed that pulse fluoro will have a lower dose rate than continuous fluoro. The dose depends on how you select the dose per pulse and the number of pulses per second. Now I'm going to say something here that might sound counterintuitive. And what I'm going to say is you really must increase the dose per pulse as the pulse rate is decreased. So often people will say, okay, we operate at 15 pulses per second, and we're going to decide to go to a low dose mode that has 7.5 pulses per second. If you do that and you don't increase the dose per pulse at all, then it's going to be those images from the 7.5 pulse per second are going to be quite noisy, and you might not get buy-in from the operator, from the radiologist or cardiologist. So what you need to do is bump up the dose per pulse a little bit, not double it, but a little bit. And there is some rules of thumb for how to do this. So what this is going to do is counter the increased noise as the pulse rate is decreased. And it has the bonus of improving the quality of a last image hold when you're just stopping and looking at the last image without any X-rays on anymore. This will give you a low noise image, and a short pulse exposure time will reduce your image blurring. If you do all this, it's more likely the operator will actually use the reduced pulse rate. So I think that's pretty important. Other dose reduction methods include collimating the X-ray beam to the area of interest, which is going to give you less dose to the patient and less scatter to everybody around. Using last image hold when you're just thinking about things and not actually moving something within the patient means no dose to anybody during that time. And then, crucially, selection of the right operational mode for the procedure and task at hand. So I'm going to just show in the next couple of slides that there actually are a really wide range of features in these machines, and you have to balance these out to use them for specific tasks. So for example, one manufacturer's fluoro unit offered all the following: acquisition rates from 0.5, 1, 2, 3, 4, 7.5, 10, 15, or 30 images per second. A lot of choices there. a lot of choices in X-ray pulse width, very big range here. Then a lot of differences in adit filtration. And the dose rates at the detector themselves actually could be chosen to range by a factor of 36. So really a lot of choices here. We also have automatic exposure control, which is going to modify exposure parameters, the KV, the MA, the pulse width, the adit filtration, as a function of what you select as a protocol, your mode selected in Fluoro, whether it's going to be your low mode, your normal mode, or your high mode, whether you're in cine, digital subtraction, angiography, or whatever, what field of view you're using, what pulse rate you're using, what the absorption of the body is doing. So the patient dose is going to be a function of the parameters selected, and the patient dose is then going to be related to the dose to everybody in the room, because there's going to be more scatter as more patient dose occurs. It's important to have some patient dose metrics. So there are two things we're concerned about. We're specifically concerned about radiation burns or skin burns, and we're also concerned about the risk of inducing cancer in our patients. So the first one, which is a cumulative air kerma area product, which is P sub Ka, which could be your kerma area product, CAP, or your dose area product, DAP, is used for quality assurance. You use that in comparison with reference values for that particular procedure. So you compare what you're doing with your group of patients with what other people have published as reasonable reference values in terms of these, say, CAP or DAP values. And then you can say, if we're keeping below those reference values, then we're being reasonably safe. We're giving them a reasonably low risk of inducing cancer. However, if we have some outliers that are above, we can also investigate those. We can say, well, why did those exceed our reference values? Say, was it because it was a very complicated procedure? Was it because the operator didn't have enough experience? Maybe they were a new resident, they didn't have experience with operating the machine, they need some additional training. So you can investigate those things, but you need the reference values and the comparison, or otherwise you don't know where you're sitting. You don't know whether you're being operating safely for the patient. The second thing that you might use is a cumulative air kerma CK at what's called the interventional reference point, or IRP, and that's used to monitor skin exposure. That's a pretty simple concept. The CK is the incident air kerma accumulated at this interventional reference point, and the IRP is just a point assumed to represent the patient's skin at the X-ray beam entrance. So this point is just located along the central ray of the X-ray beam at 15 centimeters from the isocenter toward the focal point. So basically this point. So it's just a standard point where we can evaluate air kerma, which is related to dose, to the skin. If you're going to reduce skin injuries, you need to periodically measure things on your equipment and in your studies, and it's important to have trigger values. So any new equipment or any new procedure you're going through, you want to label a trigger value in terms of a value available to the user that's easy to get during the procedure. It could be CK to the IRP, or it could be kerma air product, could be dose area product rather, could be adopted, and this could give your operator warning. Also, if procedures are repeated on the same patient, you need to be aware of that, because now maybe you're sending the beam through the same area of skin. That skin could have been damaged previously. Now you're more likely to cause a skin burn. And you should have a follow-up protocol for patients who could have received high skin dose. Now, the IAEA, which is the International Atomic Energy Agency, has suggested a number of trigger values. You could select others. These are fairly simple ones that they use. So for example, these are values where they're going to follow up patients if these trigger values are exceeded. For example, if fluoroscopy time is greater than 60 minutes, they would follow a patient. If the CAP or DAP is greater than 500 gray centimeters squared, they will follow that patient. Again, if the air kerma is greater than 5 gray, they will follow the patient. If the if they actually measure peak skin dose greater than 3 gray, they will follow the patient. If they have a lot of cine runs greater than 20, they'll follow the patient. There are other trigger events that they also use to follow patients. If they actually see a skin burn, if they see that it was the wrong patient that you did this procedure on, or you did the wrong procedure, or it turns out they had an unknown pregnancy at the time of the procedure, or if they just had multiple procedures within 12 months, which makes you more suspicious of overlap of areas, they would follow these patients. They don't do a heck of a lot. They just call the patients, they find out whether there's any skin reddening, any itching in the port area where the radiation entered, and they follow them for a year or more. Okay, so the next few slides provide background and guidance on protection in the fluoro suite based on IAEA training material. Again, going back to basics. So you know you have an X-ray tube, X-rays are coming out, the beam hits an object, in this case the patient, and on the entrance surface, that's where much of the scatter is going to be. So if we look at it, if we had 1,000 photons reaching the patient, there's going to be 100 to 200 scattered, most of them back here. Only about 20 of the 1,000 are going to come here, and the rest are going to be absorbed. Now, the absorbed stuff is giving radiation dose to the patient. Scatter X-rays obey that inverse square law, so distance will really help you in terms of your own safety. The scatter is mainly directed toward the source. This is something not everybody realizes. Sometimes they think, oh, no, the beam's pointed this way, I shouldn't be over here. Well, in fact, basically very little radiation comes on the other side of the X-ray detector. So, for U.S. staff, the main source is the patient and its scattered radiation. It's important to realize that scattered radiation is not uniform around the patient, but that the dose rate around the patient is actually a complex factor, a complex function of a lot of factors. So it's not easy to figure out right away. You need to understand this, though. X-ray tube, image receptor. Don't stand on the side with the X-ray tube. Stand on the side with the image receptor when you have a choice. Other factors that are going to affect the dose to staff. The height of the staff. You might think, well, that's crazy, but it's just the way it is. There's a different distribution of radiation versus height over the patient. If you're taller, you're going to get a different distribution of radiation dose than if you're a smaller or a shorter person. Your relative position with respect to the patient is crucial. The further away, the less the dose. How big the patient volume is that was actually irradiated. Smaller volume, smaller dose to everybody around. The X-ray tube position should be under table. That's a lot easier to shield. That's going to reduce dose. Then a bunch of things like KV, MA, and time are, of course, crucial for your own radiation dose. And then effective use of whatever shielding is available, whether it's articulated shielding from the ceiling or protective goggles, those things can help you. Now, this is the angle dependence issue and issue about height of the staff. So if you, in this particular case, we have the X-ray beam coming from the top. We've got backscatter here. You can see that's actually a higher exposure rate higher up than it is lower. So if we actually had a shorter person here, they'd actually be getting a lower exposure rate, say, to their eyes than a taller person, which is a little bit counterintuitive. Second one is field size dependence. So if you have a small field size, like 11 by 11 centimeters squared, in this case you get about 0.8 milligray per hour at this point. If we bump it up to 17 by 17 centimeter, we're up to 1.3 milligray per hour. So you can see reducing the field size, if that's possible, will reduce the scatter to the areas around. So that's really a fairly important thing to do. So you don't want to just have an open beam, you want to collimate down to the area of interest. Obviously that's not always possible depending on the procedure. Distance is your friend. So if you look at this, here at 0.5 meters away, you got 3.2 milligray per hour. If you go just another a half meter away to 1 meter, you're down to 0.8. So that's a fantastic reduction in dose rate and made yourself a lot safer just by standing back like half a step. So this is really a great advantage and should be taken, you should take advantage where possible. A key one is where that detector and where the X-ray tube is. So the best configuration is the detector above the patient and the X-ray tube under the patient. So the X-ray tube down. Now, with X-ray tube up and detector down, you're going to have, X-ray tube pointing up is, my apologies. You want the X-ray tube under the table. Saves you a factor of 3. The undercoach position reduces in general any high dose rates to your eye lens. And that's really a pretty important thing. Something to consider is, okay, large patients. If you have a larger patient, you're going to have more skin dose and you're going to have more scattered radiation. Just a fact of life. You need to bump up the power in the X-ray tube to get through the patient. You're going to have a lot more scatter. So if you just look at that in the very simplest case, you have a thin patient on this side, you have a thick patient on this side, otherwise the same geometry. You can see that the patient's skin here is closer to the X-ray tube. Therefore, you're going to have a higher dose rate. As well, the automatic exposure control is going to have to boost up the number of X-rays coming through here to get through this thickness. So again, you're going to have a higher dose rate here. That's going to mean more scatter to all around here. So thicker patients, more dangerous for everybody around, higher dose to the patient. Now, big issue is you can make a thin patient thick by just rotating the beam. So if you have, in this case, you have a fairly thin patient, but if you actually rotated the beam, you can make even that patient into a thick patient, in essence, by having the path length through them longer. So in this case, we went from 20 to 40 milligray per minute, way up to 250 milligray per minute, basically by rotating. So that's not great, and in that case, sometimes we see things like this, skin burns in patients. And if we look at that in a little bit more detail, and this was done by Kuzma et al. Back in 1999, if we look at different projections, and we look at the fluoro entrance rate first, we can see variation from 19 milligray per minute all the way up to 99, depending on our angle. So just with the same patient, we could change our entrance dose rate by basically a factor of 5. So that's quite a large factor to consider. Now, I'd like to also point out cine entrance dose rates. They would also go on the same type of thing versus angle, but now they're like 10 times or more in terms of exposure rate than the ordinary fluoro. So that's a major issue. And I'd like to point out a couple of things. You need to pay attention to the angle used. You need a great reason for cine runs. You want a good reason. You don't want it just because you like the pictures. And then finally, I'd like to comment that there's what's called an LD50, which is the lethal dose for 50. The whole body dose required to kill 50% of those exposed is only about 4,500 milligram. Cine's not exposing the whole body. But if it were, and you did it for 4 minutes, you have the potential to actually have a lethal dose to the patient. It's not, obviously it's not doing that. It's doing a small area of the body, but it can provide lethal levels of dose to areas of the skin in only a few minutes. So let's be careful with cine. Now, as an example of this is a complex procedure can certainly lead to high skin dose. And this is a patient where there was a buildup of dose for a steeply angled high dose rate beam through a large patient, and it wasn't recognized. During the procedure, they didn't recognize the dose rate they were giving, and therefore they had some problems, and it required a skin graft. So that, now, always need to state when you see something like this, well, this is quite possibly a life-saving procedure they were undertaking, so the fact they had to have a skin graft afterwards is not necessarily terrible, but if it could have been avoided, certainly we want to avoid it. So again, Fluoroscopy skin dose. 30 milligray per minute, not unusual. After 5 minutes, patient skin dose would be 150 milligray. 2 gray in 65 minutes skin damage could occur. So that's 65 minutes of fluoro, ordinary levels, skin damage. And it certainly could be a lot worse depending on angle. Do want to point out that radiation effects on the skin can be really quite complex. So what we plotted here is the dose to the skin and then the time after the exposure, and these are the various effects that can occur. So early on, maybe within a day, you might see some skin reddening. But as far as a year later, it's possible you can get some pretty significant ill effects occurring. It's possible that those effects might not even be recognized as due to radiation because it's due to something that happened a year before. So it's important to follow patients where you have the possibility of these ill effects. And here's an example. This is probably something many of you would have seen. It's a fairly famous because it's a published, there aren't that many published figures like this, fortunately. So early on, this patient had a bit of skin reddening. After about 16 to 21 weeks, it actually appeared to heal. But then 18 to 21 months after this occurred, which this is a close-up in D, and we had a pretty severe ill effect. Now, again, if this patient had not been followed, the patient may not have even realized this was due to radiation. A lot of the patients don't realize that the X-ray beam is entering through their back. They're not always told about this. Certainly, the patient survived. They had skin graft. They did okay. But if we can avoid this type of effect, I think we should try to avoid this type of effect. There are also accidents that can happen. So in this case, the patient actually rested her arm on the X-ray tube port, and nobody noticed because her arm was under the drape. And I know this is unlikely to happen, but we do drape these patients pretty severely, and you might not see what's going on underneath the drapes. You want to be careful that they're not letting an arm rest on the X-ray port where they could get a really severe level of dose. So the recommendations for this then are to establish some procedures and protocols for how you're going to image and what you're going to do in terms of following patients. You'd like to determine your dose rates for the various operating modes. You want to assess each protocol to see whether there's actually any likelihood or risk of radiation injury. You'd like to modify the protocols to use equipment to reduce dose to skin where you can, and then record the details of procedures to allow for assessment of dose later. Make it easy on yourself. You don't want to have to reconstruct this every time something happens from first principles. Let's make it easy from the beginning to figure out what dose was to the skin and what the whole body dose was. So, summary there on patient protection. You'd like to use optimal settings to reduce your dose. Use the lowest dose mode possible, and pulsed method is a good idea if you use it optimally in a way that people are actually going to use it. You want to ensure the patient is closer to the image detector than to the X-ray tube. You want to keep the beam moving if you can. So if it's possible to go through, if it's a long procedure, if you can go to a different area of the skin to be exposed, that's a good idea. All of those will lower your patient dose. Other issue that will definitely affect patient dose is whether you're using the high dose rate mode. That can certainly increase the dose rate by a factor of 2 or more. So avoiding that where you can is a great idea. The anti-scatter grid can give you better images, but it can increase the dose by a factor of 2 to 6. So you want to find out, well, do I really need that anti-scatter grid in this situation, or are my images good enough without it? Certainly sometimes the anti-scatter grid is entirely appropriate. Other thing that you should be aware of is the distribution of dose in the room, and then figuring out where everybody's going to be positioned in the room with respect to dose. So there's 3 configurations shown. First of all, they're all showing the X-ray tube below the patient, and that's correct. The detector should be as close to the patient as possible, so we're going to move that as close as possible. And the X-ray tube should be pointed toward the operator if possible. So we want this. Now, why do we want this one in the bottom right? Well, if you look at basically it's these 2 choices on the bottom. A lot of the time I find that people say, well, I don't want to have that detector near my head because I think I'm getting scatter from the detector. But measurements actually show that if the X-ray tube is pointing towards you, you get less dose to your head and to your eyes, so that yellow area. So that is an advantage. One of the things this does point out, though, is we want lead that actually comes down a fair distance here. You don't want any short skirt here because you don't want X-rays impinging your legs and lower body if you can avoid it. So this is our best way of doing it. We do want to have good lead protection there. Shielding and dosimetry are in fact critical in fluoroscopy. So shielding, you have lead curtains that can be installed on the patient table. They're not always installed. Sometimes they get broken. Replace them. If you have to work on the other side of the table, get them on both sides of the table. Lead aprons should always be worn, and you have to cover your thyroid, your core, and reproductive area. I don't show a very good example over here because this is kind of heavy. You'd like to have one that is in 2 sections so that the weight is on your hips as well as on your shoulders. Lead glass screens would be great for absorbing and scatter radiation, and wherever possible, I recommend goggles to protect the eyes. Now I'm going to say caution on one bit of radiation thing, and that's the, on one protective thing, and that's lead equivalent gloves. They're not always beneficial. If you put your hands in the primary beam, then the automatic exposure control is very likely going to boost up the radiation to the patient and to everybody in the room. So just be very careful about getting your even your lead protected hands into the primary beam. Again, radiation shielding. So here's our detector. Here's our ceiling mounted radiation protection screen. Use it if you can. If it's not in your way, that's a great, it's much more effective than goggles. These things are really good for shielding, and because your X-ray tube's underneath, it's nice to be able to shield that tube underneath. Again, I like to focus on iDose a little bit today, and one of the issues on iDose is how we operate. So if you look at this guy, if you look at the scatter that's coming up from here, if he's looking up towards this thing, the monitor, as he's looking upward, the area, it's easy for radiation to sort of duck underneath his lead goggles and get to his eyes. So X-ray scatter is mostly coming from below. It's better not to have to look up all the time. So it's not ideal to have these guys here, these monitors there. If it's possible just to look straight forward, that's a little bit better for eye protection. And that was shown by these guys, Gerber et al. At London University, where they evaluated a bunch of different types of protective eyewear, and they had a couple of findings. One, that there's really substantial differences among different types of protective eyewear. And 2, that it's really essential that gaps be minimized and eyewear mold around the face of the person in question. So everybody should have their own well-fitted eyewear. And part of these things is, let's just look at this. The front, the lower numbers are better. These are not too bad. But from below, some of these are really bad because it's hard to get shielding from below. So if you're looking up, that radiation can get to your eyes more easily, even with the goggles. Other things you're going to need are dosimetry. So you should have one dosimeter worn underneath the apron. You don't want to confuse that with your other one. You may wear a ring or bracelet dosimeter if you're concerned about dose to your hands. Normally you don't worry about that in fluoroscopy, but if you are actually a person who has to palpate a lot near the beam, then you might want to have a ring or bracelet dosimeter. One dosimeter should be worn at the collar above the apron to measure radiation to the eyes. Now, in summary, fluoroscopy may lead to high radiation dose to patients and really pretty significant radiation dose to staff. Modern fluoro units really offer a lot of options, so you have to select ones that can meet clinical objectives while maintaining low dose, and that's a non-trivial task. So take your time, work with your the people from the manufacturer, work with your internal experts, whether it's a medical physicist, whoever you have there, because that's really going to help you in the long term. Reducing patient dose will often reduce scatter dose to staff, so it's in your self-interest to reduce the patient dose. Keep the X-ray tube at a maximal distance from the patient. Use high kVp where possible. Wear your protective aprons and radiation monitors. Know where the scatter is highest in the area. Keep your distance as far as is practical. Now, there are a bunch of websites that give you very useful information. I'm going to point out Canada Safe Imaging. They're really great. They're starting to provide more information. We can certainly be contacted at our website. I would point out the one at the bottom, which is very interesting organization, Safe Radiology from the IAEA. You might want to take a look at that. There are a number of organizations, including Canada Safe Imaging and ourselves, are quite interested in reducing dose to staff and to patients. So I'd like to thank you for listening, and I'm going to just take a look and see if you had any questions. I hope that it has been of benefit to you. Okay. Okay, so I have a question here. Are there any guidelines for what level of exposure to the eye lead glasses go from being recommended to mandatory? So that will be somewhat dependent upon where you're, well, it is dependent on what province you're working in. But if you're getting close to the regulatory limit, then clearly you'd need eye protection. The regulatory limit in most provinces now is 150 milligray or millisieverts per year. That's going to go to 20 millisieverts per year in the relatively near future. So I would say if you are getting close at all to 20 millisieverts per year to your eyes, then you certainly should have lead glasses, and they aren't mandatory now, but they will be mandatory in the relatively near future, depending on your province. Oh, I apologize. One comment it was that I should add, and I certainly it's a mistake on my point. I should have added the Canadian Radiation Protection Association website, the www.crpa-acrp.ca as another site. There's certainly a crucial group of experts in radiation safety that should be added. Okay, there's another question. Okay, you mentioned that increasing pulse should also, no, sorry, what I meant was decreasing pulse rate is what would reduce dose. So, sorry, the question is, you mentioned that increasing pulse should also be followed by an increase in output per dose, but not quite doable. You said there was a rule of thumb. Can you share? The rule of thumb is a little bit more complicated than just saying it. I can provide that information, but what you do is you reduce the number of pulses per second, and you slightly increase the dose per pulse. Now, the slight increase is there is a rule. There's a medical physics paper from a few years ago that does give us some information on that. I can try to append that to the mailing for people. Okay, can you recommend a good reference for diagnostic reference levels in the Canadian context? I don't believe I have a Canadian reference for that. Sorry, I don't have a Canadian one. I think the IAEA SafeRad website, which is a mainly European site, does have appropriate ones for many fluoroscopic procedures. And there are DRL ones within Safety Code 35 for ordinary X-rays. I don't think they have much for fluoroscopy, however. Okay, other question. Can you define radiation worker? Who should wear a dosimeter? That's a little tricky, and it's by province. Most provinces, however, will say if there's a possibility that you would exceed the level of the general public, or if there's any possibility of that, then you should wear a dosimeter. Most provinces, again, interpret that if you are entering a fluoroscopic room during a fluoroscopic procedure, then you should be defined as a radiation worker because of the possibility that you could exceed the limit for a worker. I know that is a little wishy-washy, and the problem that comes up here, as I think you might recognize, is nurses in operating rooms. If you talk to some regulators, they will say every single nurse who ever enters the operating room has to have a dosimeter. If you only enter an operating room once per year, that seems excessive. But I would ask your radiation protection officer at your site for their own advice, or you can call us and let me know what province you're in. I can try to give you some guidelines. Okay, is there a way to convert air kerma or DAP, which is what our fluoro unit measures, to skin dose? We currently have our medical physicists working on this for our cath lab. A short answer is yes, but it's actually not the best way of doing it. I can, again, I think I might be able to give a better answer to some of this I'll try to answer that more completely in a email, which goes out to all the users, all the people who've registered. And I think I have. I think I've answered all the questions that were there. If I haven't, I apologize, and I'll look for them afterwards. Thank you for listening, and hope that this has been of benefit to you. We'll be presenting a few others in the near future. And again, thanks for listening, and I think this is the end of my presentation. Thanks very much.